We've learned about Newton's first law, which was inertia. We have learned about Newton's second law, which is the proportion of mass and acceleration to make force. Now we are going to learn about Newton's third law, which is for every action there is an equal and opposite reaction. Newton's third law is the basis for all rockets. So in this rocket here, we have fuel being burnt. What ends up happening though is when it's burnt, it needs some place to go as it expands and it forces its way out with great force. So here is my action, the fuel or the gas being burnt and expanding and forcing its way out, creating a force. My reaction is the rocket moving in the opposite direction, moving up. Same idea as if we step off a skateboard. My action is moving forward, stepping off the skateboard. My reaction would be the skateboard moving in the opposite direction. Newton's third law is also why firefighters practice with a fire hose in groups of two. It's because the water comes out with immense force shooting out in this direction that there's going to be an immense force also, an equal force in the opposite direction. And in order to brace for that force, you'll need both firefighters there to brace for it. Otherwise, you could get something like this, which is a little bit exaggerated, but that you get the point. So let's take a look at my first example of Newton's third law. In the following example, an applied force acts on box A, causing all three boxes to accelerate. Newton's third law is used to calculate the force that box C exerts on box B. So before I go into solving this question, there's one thing we have to clarify up here. Because sometimes students think, well, if for every action there's an equal and opposite reaction, how does something move? Well, that's because we look at that Newton's third law in different pieces or systems. So we're first going to look at this first guy here. Let's say he's applying 100 newtons of force. So this man's applying 100 newtons of force on block A. So block A exerts 100 newtons force back on him. Then we would look at block A separately, and then with its system, and then block B, and then finally block C. Now in this question, the boxes are moving to the right with an acceleration of 1.5 meters per second squared. We want to calculate the force exerted on box B by C. So we know my total mass of the system is 23 kilograms, and we can find the force of the total force moved throughout. But we just want to know what force box C exerts on box B. So to do that, we're going to look at box C exclusively here and make a free body diagram for box C, which will look something like this. Okay. Now in this part here, remember my normal force and force of gravity are going to balance out. Now let's look at what is given. So here we have a mass A is 8 kilograms, mass B is 10 kilograms, mass C is 5 kilograms, and my acceleration is 1.5 meters per second squared. Now in order to calculate for mass C to accelerate at 1.5 meters per second squared, we have to use Newton's second law, which is force is equal to ma. So we end up getting my mass of 5.0 multiplied by 1.5, which ends up giving us altogether 7 newtons to the right. We know now that if block C has 7.5 newtons applied to it to the right, that must mean it must give 7.5 newtons back on block B, which is 7.5 newtons to the left. So let's take a look at my second part of this question. We want to know what is the force that box B exerts on box A. So for this, we're going to consider a free body diagram on box A. But one thing first is we know that since Fn is going to be equal to Fg, since these boxes aren't falling down, there's no y movement, all the movement's in the x. We're still going to put in those forces, but we have to really focus on my x-axis here. So in this case, I know my force of B on A is pushing A back. We know my applied force is pushing A forward. So in this case here, we could say my net force is equal to applied force minus the force of B on A. Now my force applied must be bigger or big enough to move all 23 kilograms at 1.5 meters per second, because A is the first block in that system. We know my net force is used to accelerate 15 kilograms at 1.5 meters per second, because that is the force needed to move blocks B and C. So if we go back here, let's look at this. My total system is 23 kilograms. So we have to move, the applied force is all 23 kilograms moving, and then we have blocks B and C, which is 15 kilograms, and that's going to be the net force to push these. So if we continue this formula, we know that my F net is the mass of blocks B and C multiplied by acceleration is equal to my applied force, which is the mass of the whole system multiplied by my acceleration, and then we're going to subtract it by the force of B on A. So we end up getting here, we have 15 times 1.5, which is equal to 23 times 1.5, and then we want to subtract the force of B on A, which gives me a force of 12 newtons for B on A. So in our second example, we are going to be adding friction to our system. In this question, we have two boxes, A and B, are on a rough surface. An applied force causes both boxes to accelerate at 2.6 meters per second squared. If the force of friction on box B is 28.3 newtons, calculate the exerted force by box B on A. So once again here, we are going to look at a free body diagram on box B, because we want to figure out what box B is pushing back on A. So let's take a look at my free body diagram here. Once again, it's not moving up and down, so the normal force and my gravitational forces are equal. But one thing to look at here is my applied force is actually going to be bigger than my force of friction. But if we're looking at what is being pushed on block B from this, block B has to overcome the force of friction and the applied force. So in this case, we look at it, my net force is equal to, once again, my applied force minus the force of friction. So my net force is must be big enough to accelerate all of block B, which is 8.5 kilograms, at 2.6 meters per second squared. My applied force is the force that B exerts on A. So if I rearrange this, I'm going to get my applied force is equal to my force of friction plus my net force. So in other words, I know that my force applied, which is A on B, is going to be equal to my net force plus my force of friction. So now that means force of A on B is equal to the mass of B multiplied by acceleration plus my force of friction. We end up getting 8.5 multiplied by 2.6 minus 28.3, which gives me 15 newtons left, is the force applied of A on B. So in our last example in this video, we are going to be dealing with a system that involves masses and tension and rope. So we want to calculate the acceleration of this system. So my first hint is we need to find the acceleration and treat the system as a whole. So in this case here, I have 3 carts which we have to add the masses to. So I'm going to use Newton's second law again, where we have force is equal to mass times acceleration. We know my force is equal to 6, so then, and my 3 masses is equal to 3 combined, so I get 6 is equal to 3 times A. We end up getting a total of an acceleration of 2 meters per second squared. So now I want to know, what is the force for each rope, rope 2 and 3, to withstand? So to help me out with this, I'm going to draw a free body diagram for my 3 boxes. So then for box C, I end up getting a free body diagram where my normal and gravitational force are equal because there is no movement in the Y, but we only have a force of B on C. This force of B on C will be most likely my tension in the rope. Then let's look at box B. For box B, I have the same thing. My y, my normal force and gravitational force are going to be the same. But in this case, I have F of B on C, and I have the force of A on B. Now the force of A and B must be greater because that's also moving the other system. Then on box A, I have once again my normal and gravitational forces are equal, but in this case I have 6 newtons is going to be greater than the force of A on B. So let's start with rope 3. I know that for rope 3, the tension of it is right here. This is what's pulling box C, so it's the force of B on C. So rope 3 must be able to withstand the movement or the acceleration of 1 kilogram at 2 meters per second. So my F net is going to be equivalent to B on C. B on C is the force in rope 3, which is the same thing as tension. In this case, I'm going to have my force is equal to mass times acceleration, which is the same thing as 1 times 2, which is 2 newtons. So now let's look at box B. So box B deals with rope 2. In this case here, we know my F net is going to be equal to the force of A on B minus the force of B on C. So I end up getting my F net is equal to force of A on B, which is equal to force of B on C. Now there's some things here important. So my F net is the result of just mass, B, and the acceleration. Whereas my F A and B is the force in rope 2. And my force B on C, we figured out through looking at the part of box C. So now when I continue this, I could go, my mass times acceleration is equal to the force of A on B minus the force of B on C, which gives me 1.5 times 2 is equal to force of A on B, which is going to be my rope, minus 2. So then I end up getting 3 is equal to force of A and B minus 2, which is going to be give me 5 newtons on A and B. Therefore, my tension in rope 2 is going to be 5 newtons.